ranking task. Rank from least to greatest the acceleration and net force of these 6 different Atwood machines. Well, the first thing I think I'm going to do here with all of that data is I'm just going to solve it generally without plugging in the values. So what I'm going to do is I'm going to do this one from a systems approach. Let's draw our systems. We'll call this on the left M1. That one on the right is M2. And we'll define our system. Let's say M1 is that way, so we'll call that our plus y direction. We'll define our system like we did with our alternate solution earlier, just to change things up, as looking like that. So when I do that, the net force in the y direction, we're going to have m1g in the positive y direction minus m2g, and all of that has to be equal to ma, where our total mass is m1 plus m2a. Or acceleration is going to be our net force in the y divided by m1 plus m2. And the net force is just m1g minus m2g, or net force will be equal to g times m1 minus m2. Now, with all this different data, it seems to me the easiest way to handle it might be to make a table. So let's do that. We'll have a row for A, B, C, D, E, and F. Our data will have a value for mass 1, a value for mass 2. Once we have those, we can calculate the net force by multiplying g times the difference of those. So let's make a column for net force. And then we finally need to know the acceleration. Let's make a column for acceleration, which will be the net force divided by the sum of m1 and m2. So then we can just start filling in our data. For situation A, m1 is 5, m2 is 1. All right, so the net force is going to be m1 minus m2, 4 times g10, or 40. And the acceleration is going to be the net force divided by the total mass, 40 over 6, which is 6.67. So I can just keep filling in the rows of my table in that manner. So for B, we have m1 is 3, m2 is 1. So the net force is going to be the difference of those times 10, or 20. And the acceleration, 20 divided by 4, or 5 meters per second squared. For C, mass 1 is 4, mass 2 is 2. So again, we'll have a net force of 20, but our acceleration is going to be 20 divided by the total mass 6, or in this case, 3.33. For D, we have initial mass m1 is 1, m2 is 4. So the magnitude of the net force, 4 minus 1 is 3 times 10, is going to give us 30 newtons. 30 divided by the total mass, 5, will be 6 meters per second squared. For part E, 1 and 2 for our masses. So our net force is just going to be 10. In our acceleration, 10 divided by our total mass of 3 is just 3 1/3. And finally, for F, we have 8 as our first mass, 2 as our second mass, so the difference is 6 times 10 will give us 60 newtons for our force. And our acceleration, 60 divided by 10, or 6 meters per second squared. So now we're asked to rank these from least to greatest for acceleration and for net force. So now I just use my table to rank them from least to greatest for acceleration. Looks like we have C and E together, so those are the smallest. Then we go up to B. Then it looks like D and F are both 6. Those are together. And finally, our highest acceleration, A. Same thing for the net force. It looks like our starting point is E, our lowest. Then B and C are both 20. Then we come to D, 30. Then we come to A, 40, and our highest net force, F, with 60 newtons. All right, hopefully that gets you a good start with Atwood machines, gets you feeling comfortable with them, and lots more practice with Newton's second law and how you would apply that with free body diagrams and pseudo free body diagrams. Thank you so much for watching Educator.com. We'll see you again soon.